Thank you very much. Yeah, sorry for that, but we are short of time, so I simply start off. So welcome and thanks for coming for my presentation today on future developments in refrigeration technology. And as I come from heat pumping, so it's thinking about the heat. So my name is Stefan Enninger. I'm Solution Manager for Industrial and Large-Scale Heat Pumps at the company Johnson Controls. And I was formerly in research and development, and my motivation is now to develop and implement the necessary solution for higher efficiency, because now is the time to change to mitigate climate and climate protection. So I give a brief overview on Johnson Controls in Germany and give some basic considerations and definitions, followed by very easy steps. So there's not rocket science, but easy steps to adapt for future and higher efficiency in your cooling processes. So first, for Johnson Controls in Germany, we are a huge branch on fire prevention, detection, security solutions. And beside that, I come from the branch from industrial refrigeration and heat pumps, and also from the HVAC equipment with our brands Sapro, York and Frick, when we have also a booth in Hall 7. So I come from this small piece of cake, and I want to show you that we are located all over Germany with more than 950 service technicians, so we can easily fulfill any service demands all over Germany. And the important vertical markets we are serving from the HVAC and industrial refrigeration system is in the industrial manufacturing, energy supply, utilities, district heating, for example, but also healthcare and retail. So some basic considerations and definitions. So I don't know if you're all familiar with heat pumping or chilling. I hope so, but this is one slide to the general basic considerations. So this is depicted a very simple refrigeration cycle. So we have here the evaporation, we have the compression, and then we have the condensation and the expansion again. So very simple. And in case of a chilling, the useful cold is delivered here by the evaporation, and you have a heat rejection on the other side. And therefore the EER is the definition of the energy efficiency ratio, which is the cooling, the useful cooling divided by the electrical effort. If you are talking about a heat pump, the useful heat is on the condenser side, and we are talking about a COP, a coefficient of performance, which is the useful heat divided by the electrical consumption. And the heating supply can be district heating, buildings, or process heat. On the other side, process cooling, data center cooling, floor cooling, or AC. And if you put both together, you have the total energy efficiency ratio. So we have the heating, useful heating, and useful cooling divided by the electrical effort. So keep that in mind. The TER, this is a very important number. I will stress this out a little bit more. But now to the very easy steps. Again, the initial situation by our customers coming from the industry, we have always the same installations, and typically they are often historically grown. So in large-scale industrial solutions, we have a central combined cycle gas turbine, and power plant, and the steam extraction. Steam extraction to fire a steam network to fulfill process heat demand, for example, 130 degrees Celsius. If you have a medium-scale industrial solution, this is simply a gas burner. The pressure and the temperature of the steam network is set by your highest consumer, typically. And what comes to my mind is that heat and cold is simply separated. This is considered separately. So you have the heat provided on top, and you have the cooling provided below. And this is a chiller, and here you have the gas burner, and beside you have a massive amount of rejected heat which can be used. And typically you have centralized chiller with fixed temperature, and this is also set by the minimal necessary consumer, although there might be a cooling demand in process equipment which is even higher. The cooling network is driven at the lowest temperature available. So you have to rethink a little bit on that. So typically the customer wants to do not change the system, but if you want to go to higher efficiency, you have to reconsider your process. You have to use a 360 view on all of your buildings, process, demands, and so on. And you can save money and CO2 emission massively. And I have some examples here. So first of all, this is a very low-hanging fruit. Reconsider the temperatures. So if you increase the evaporation temperature or lower the condensation temperature, you can gain immediately 3%. So simply, this is not rocket science. For example, if you enhance the evaporation by 1 Kelvin, the energy efficiency ratio increases by 3%, saving money and CO2 emission. That's really simple. And I've calculated this here. If you go even higher, you're going up to 7%. And even if you can manage to go even higher to 10 degrees Celsius, for example, outlet temperature by evaporation F8, you have 14% increase directly with the same equipment. So this is calculated with a chill pack from our company, a unit with an SMC compressor. This is the same unit, the same equipment, but running at higher temperatures. And you save money.
Yeah.
If you retrofit further your motors with a higher efficiency motor or the compressor with a variable speed drive, you can gain another 10% of efficiency increase. And if you split temperature levels or do multi-compressor installations to cover low temperature demands, there is another option to increase massively. For example, the energy efficiency ratio can easily increase to 7 if you provide your cooling network at higher temperature level and install local booster chillers for the real low cooling demand. And this is not theory, but I have here a practical retrofit example by our customer where the cooling demand was 10 megawatt. This was fulfilled by one system before. So what we've done here, we have done covering by 3 compressor units, so 3 compressor units in parallel, serving each 3.5 megawatt at 2 evaporators in parallel for better part load regulation. Because typically you have a part load, a huge amount of part load during operation. We equipped the compressors with a variable speed drive and high efficiency motors and an oversized oil separator to keep temperatures very low, which is also gain in efficiency. And then we were able to reduce also the delta G, the temperature reduction, by simply optimize our heat exchanger, so for direct refrigerant condensation, and we oversized the condensers a little bit, which is a higher capex for sure, so you're paying more money because it's oversized, but on the long run, it saves money tremendously because you're saving operating costs. So we were able to have a capacity of 12 megawatt at 33 degrees Celsius. And the system was designed to operate even with very low condensation temperatures. During transitional seasons, we have condensation available at 16 degrees by these oversized condensers, which gives you a push in your COP. On the evaporator side, we were also able to reduce the delta T simply by design rules, by oversizing, by having a direct evaporation. So still serving the 12.6 cooling network by evaporation at 3.5 degrees Celsius. So this was a really nice example, running now and saving the customers more than 10% of operating cost per year. Okay, coming to a next step. So reconsider heat rejection. So typically the heat rejection is not used in cooling application, but if you have typically also a heating demand, for example floor heating, this is useful heat. So again, this is the same system where I changed the numbers of the condensation. So this is a chill pack running a typical cooling and condensation temperature of 38 degrees Celsius, giving you a very nice energy efficiency ratio of 5, serving a cooling network of 6 degrees Celsius and a capacity of roughly 420 kilowatt. By changing the temperatures of the condensation up to 50, the electrical energy efficiency ratio from the chiller drops, for sure. But then you are able to use 490 kilowatt as useful heat for floor heating. And in addition, we have a combination of higher cooling temperatures, so 2 Kelvin on the cooling network, higher rejection temperatures, and usage of the hot gas from the chiller to even overcome 50 degrees Celsius to achieve 60 degrees floor heating. So you have a double usage. You have cooling demand on the cooling network, and you can easily manage a floor heating of your industrial process. And this gives you a TER. This is the number again of 9.2. For the same amount of electricity, you get heat and cool. Going further is thinking about cascading the system. So if you have a system already installed, you have typical chiller and you have your heat rejection, and you have a heat demand. Why not do a cascading by putting a cascading heat pump on top? Instead of using heat rejection, use this as a source for the heat pump. And this can deliver process heat and floor heating at very easy way. And that's again not theory. I have an example here. So this is an example from our customer at the Nestle Werk in Bissenhofen in Germany. And this was the installation. So typically we have the chillers here, the chill packs, and a cooling network, and we have a heat rejection at 38 degrees Celsius. So what we have done here, we integrated a heat pump. This is a heat pack here on the cooling side, taking the rejected heat from the chiller section, then provide process heat at 60 degrees Celsius with a COP of 5.8, because we were using rejected heat from the coolers. So that's amazing. And we were serving 2.2 megawatt heating capacity by a very simple design heat pack system. And towards our customer, this was really saving money and CO2 emissions. So the complete work, so the heat, process heat was provided for milk powder production using the waste heat. And before there was used the steam for the milk powder production, we get rid of the steam. So dramatically reduction of steam demand and reduction of CO2 emissions by 10% for the whole plant by only one installation. So 10% reduction in annual CO2 emissions by only implementing one simple cascading heat pump. This is huge numbers, right? And if you want to have a look on that, please look on the Nestle webpage. Going further is using dual usage. So if you have a possibility to have a new installation and you have process heat demand, so think about installation of a dual usage heat pump and cooling. So not simply split again heating by gas burners and cooling by a chiller, but use both. So thinking about the heat, two-stage heat pump, for example. So this is one of our dual packs serving 612 cooling network and also the floor heating at 60 degrees with a really nice COP here. And even this two-stage heat pump is able to provide process heat at higher temperatures, for example 80 degrees. So that's really attractive then, and still a very interesting COP heating of 3.35. And if we go to the TER, this is amazing. So if we go to the TER, so we are serving cooling and heat, we get a TER of nearly 7. For the same amount of electricity, you get 7 times cooling and heat. That saves money. And if you want to look and talk to me and have some more technical details, we have a real size customer manufactured dual pack shown on our booth, which will be further transported to our customer. And there you can see how it looks like, and we can discuss details there. So to sum up, I urge you to reconsider temperatures. You can easily spare money. You can easily enhance your efficiency by increasing the required temperatures, or have a deep look on the required temperatures. Furthermore, reconsider usage of the rejected heat. Use it as directly, or if not possible, use it as a source for a heat pump. And if you do a new installation, please think about a two-stage heat pump to have cooling and heating at the same time, saving CO2 emissions and money. And of course, use a 360 view on all of your buildings, processes, and temperatures needed. And still there's more to come. As you might have seen, there was always the steam which was not fulfilled by our systems, but now here the steam comes into place again. So the outlook, there's more to come. If you have waste heat here at a level of 40 or 50 degrees Celsius, you can easily heat that up to 120 degrees process heat. So this is a new product from us. It's our high temperature heat pump shown also on the booth, working with natural refrigerant hydrocarbons, so isobutane and N-butane, very reduced component design and low refrigerant charge. So if thinking about cooling and heat rejection, you can also think about process heat. So thank you very much for your attention, and I'm up to questions either here or on the booth. So you're welcome. Thank you very much.